Right. Hello. Welcome to our uh, snow day class. I've never done this in my life, so good luck to me. Good luck to you. Hope you session. And honestly, I don't know how long this will go, so we'll see. There's no time restriction, right? If you have to leave, too bad. If you can stay, we can go like 2, 3 hours. I don't know. I'll stop when I feel like it. Hopefully, you have some water beside you, some food, snacks as well. Hop on the train. Start it. So last class, we talked about the idea of differential calculus. Again, the differential calculus in one word is just change. How does change happen? Well, change happens because of the gradient. Gradient can be measured as rise over run, the delta y over delta x. Delta y, the y is just f of x, so it's delta f of x over x, delta x. Then how do we measure the change in f of x? We measure f of b minus f of a divided by b minus. That's how we measure the rise over run, as you can see in the graph here. Well, when we do that, we're taking the average gradients from A to B, the average one. We're not happy, we're not fully satisfied with the average value. So we try to go closer and closer and closer. What I mean by that is we're reducing the run. The run was B minus A, so then we reduce it all the way to, when we measure it as H now, instead of saying B minus A, that H is a step or increment, and we try to make that small and small and small. We take a limit, so limit as H goes to 0. That's called the instantaneous rate of change. Instantaneous rate of change calculates the change in f of x divided by the h value, whereas h goes to 0. We can't just do that because h cannot be 0. So that's why we take the limit, and that's basically why we learn limit, the topical limit. That's called the first principle of calculus, which kind of coincides with the idea of the tangent line. The tangent line is about the line that touches the graph at a certain point. Okay, because it touches that graph at exactly one point, the gradient of the tangent line is going to be the instantaneous rate of change of that graph. So how do we find the gradient? Well, we use the first principle of calculus, and then we know the position, a and f of a, so we can find out the equation of the line, or equation of the tangent line. So then we had this scenario practicing how do you take the limit as h goes to 0, and then we do some work, which gives us a gradient function, which we'll talk about in a second. And then we were able to find out the equation of line. So we did some practice questions as well. And the gradient function of f of x is synonymous of saying the derivative function of f of x. And how do we notate the derivative function of f of x? We either use the f prime of x, or dy over dx, or d over dx of f of x, or y prime. One thing that I just want to point out is that one thing that I will point out is that this dy over dx, this does not mean that it's dy divided by dx. So it looks like a fraction, and it kind of also acts kind of like a fraction too, but it's just not. So make sure that you realize that we're not doing a fraction actually. Okay, so you can see it on the left hand side here. The dy over dx is called the Leibniz notation. I have no idea how to pronounce that, and it's okay, you don't have to know it, but just know that we can do that. So some questions here. These are just worded differently, but they're essentially working the same thing. Find from the first principles the gradient function of f of x is, aka find the f prime x, aka find dy over dx. Okay, let's just do one example here. Let's say we're doing example for 3c. Okay, let's say we're doing y equals x cubed minus 2x squared plus 3. Then finding the dy over dx is the same as taking the limit as h goes to 0 of f of x plus h minus f of x. Again, if you want to just try it on your own, I'm writing a lot. So that will be limit as h goes to 0. F of x plus h will be x plus h cubed minus 2x plus h squared plus 3, this part, minus x cubed minus 2x squared plus 3 writing there, an h. It'll be x cubed plus 3x squared h plus 3x h squared minus 2x squared plus 4xh minus 2h squared plus 3. Phew, okay. Minus x cubed. Let's put the x cubed in the front. I'm just going to collect like terms as I go. Minus x cubed plus 2x squared. Where is that? Plus 2x squared. Then minus 3. All right. A bit complicated, but we're ready to cross out some stuff. So this goes to there. So ultimately, I only have the terms on the numerator always have some kind of h in there, which is nice. So then we can cross out h everywhere, right? As h 0, 3x squared plus 3xh plus 4x minus 2h. But then now we take the h goes to 0, so then second and fourth term will be just gone. It'll be 3x squared plus 4x, which doesn't sound so good. I think I left out a minus somewhere. Where did I make a mistake? First I left out the h cubed here. Minus 2x. Oh, the second term was minus here. My bad. Minus. That should be minus. That should be minus, and that should be. Okay. Are we all happy with this? Assuming that there's no one's hands up. Be happy with this. Now, as you can look here, this process is very tedious. And especially this is more tedious when we have more complicated polynomials or more complicated functions. So we're going to do that in a second, about five to 10 minutes. But I just wanted to see it out that we're not wanting to do this every single time. It's going to be a waste of time, and we don't have time to do this first principles every single time. So we'll try to find a more faster way to do this. Okay. Let's move on. Now we're going to the idea of the differentiability. So the differentiability, as the name implies, it's closely related to the idea of the limit exists and also the continuity and things like that. Okay? So we have to understand these three things together. Limit exists, and it's continuous, and it's differentiable. Okay? These three things are closely related. So to understand the idea of what is more superior of the other, okay, so differentiable is a bit more specific case. So analogically, this is kind of like a square kind of thing. Okay? What I mean by that is, if it's a square, then a square is rectangle, right? So you can say that continuous is kind of a rectangle thing. Is a square always a rectangle? If it's differentiable, it's always continuous. Yes. However, is a rectangle always a square? No. Then if it's continuous, is it always differentiable? Also no. Do you understand that hierarchy system? The limit exists is even a more broad concept. So we could say this is a polygon. Is a polygon always a rectangle? No. Is a rectangle always a polygon? Yeah. So if it's continuous, it's always limit exist. If it's limit exist, is it always continuous? So I just wanted to point out the hierarchy system of these three terms. Okay? You can see there in the blue box here on the left hand side, if f is differentiable at x equals a, then f is also continuous at x equals a. Okay? However, the converse, if a function is continuous at x equals a, it is not necessarily, it's not always not differentiable, but it does not imply that it's differentiable at x equals a. So, just to recap, what is the idea of limit existing? Limit exist means that the limit from the left hand side to the limit, and also the limit from the right hand side, or they are there and they're equal to, right? That's the idea of the limit exist. Continuous means that there's no hole, there's no break, and there's no jump. Differentiability talks about, has that condition of continuity as well, but then it adds in one more part. So here you can see that on the second part here, the condition is that the left-hand side derivative and also the right-hand side derivative, they do exist and they're equal to each other. Left-hand side derivative, right-hand side derivative. The idea of the left-hand derivative in our understanding of calculus is just, it only appears here. So you don't have to spend too much time understanding how this works. But I don't think it's that difficult to understand, because left-hand side derivative just takes a limit on the left-hand side. Okay, so remember that the limit can go from left to right. The same thing. This time we're just taking the h going to 0 from the left-hand side, and then the h going to 0 from the right-hand side. Okay. The definition of differentiability is that condition 1 is continuous. 2, left hand not so used to using this pen. I haven't used this. So if you meet those two conditions, if it's continuous, and if it's left-hand side equals left-hand side derivative, right-hand side derivative, and they exist and they're equal to each other, we say that the function is different. What it means by that is, so the definition on words sounds very, like sounds very abstract, right? But just like continuity, if the graph visually makes sense, it is differentiable. You'll see very clearly in a second when I try this kind of question here. So look at this graph here. It's an absolute function. F of x equals absolute value of x, which absolute value of x is just a piecewise function, right? It's a piecewise function, whereas x when x is greater than or equal to 0, and negative x if x is less than 0. For this one, however, you'll see that, okay, first of all, just a graph of it, okay? Look at the graph here. This just little bounce part. Are we happy with this? No one's happy with this? Just from the fact it is not differentiable. It is continuous because there's no hole, right? It just goes on continuously, but it's just not differentiable. A formal way to see that would be to follow along with the derivative of the left-hand side and the right-hand side. So you can see that if you take the derivative of f of x, it'll be 1 and negative 1. They're not the same at x equals 0, so they're not differentiable. However, in this example, it doesn't mean that it's not differentiable everywhere. So it is differentiable everywhere else, just at x equals 0, it is not differentiable. Why don't we try this example number 1 here. So once again, just by looking at this, I think it's quite obvious, right? I think it's quite obvious that it's clearly not differentiable, like just by looking at the graph. But then let's try to formally prove it. It wants us to tell me why it is not differentiable 0. Well, let's find the f prime of x on both. Hi, Jeffrey.
In the book, it says like it always specifies the point that it's not differentiable, but we've been saying like the function is not differentiable. Is there a difference?
So I think we say, okay, I've been colloquially saying till now for like the past couple. I've been saying that function is not differentiable if it's not differentiable at a single point. So if it has at least a single defect, then I don't think it's differentiable. But yes, specifically, just it's just not differentiable at that point. Everywhere else, it is differentiable. So let's find the piecewise function of the derivative of f of x. So fx plus 2. So now we have to do some work. So what is x plus 2? We have to differentiate it. It'll be limit as h goes to 0. X plus h 2 minus x plus divided by h minus x minus divided by h. It'll be h over h. It'll be 1. Okay, that was easy. X is greater than or equal. What about x squared plus 3x? Should I give some time to do this? I'll give you 30 seconds. Try this on your own. Okay. So, I'm just gonna do this fast, okay? It's 2x plus 3. Okay. I don't know how I did it, but I just came to my mind, okay? So it's 2x plus 3. Yay. So 2x plus 3 when x is less than 0. Okay. Well, is it differentiable at x equals 0? Then if it's x equals 0, then f prime of x is 1 when it's greater than 0. And also it's 0, 2, 0, 3, so to 0 plus 3, 3. So then, am I happy with this? No, because my f prime of negative of 0, if it's coming from the left-hand side, it's going to be, and also the f prime from positive side, it's going to be 1. We good? Not equal. Therefore, the f prime, sorry, f of x, not differentiable at x. So this is the idea of the differentiability. We're learning about the differentiability right now, because if it's not differentiable, then we can't do all the stuff that we're about to do pretty. All right. 17, not including me, 25 people. That means that 10 people who are not here are not attending the class. Ugh. Big shake. Big shake. All right. Okay. Let's not do the negativity here. Anyways, I think that concludes our chapter 16. So chapter 16 was just an introduction of differential calculus, the idea of what is differential. differential calculus, or derivative, or the f prime, or dy over dx, all mean that visually we're finding the gradient of a tangent line. Gradient of. Also, we learned about when it is differential. What? Now we know the understanding of what differential calculus is. Then we're gonna go on to chapter 17, and then we'll add some tips and tricks on how to find the derivative of a function quickly and more optimally. Okay. So let's go to the next chapter, chapter 17. Any questions before that while I write? Of differentiation. Okay. It's a very long chapter. I'm not too sure how much I can do today. Probably stop around like chain rule or maybe able to proc rule, quotient rule. Anyhow. Most of this topic stuff is in the format booklet, so don't worry too much about memorizing these steps. In one word, this chapter is just about skills or tools of how to find derivative. Practice pronouncing that. Derivative. Let's move on. Okay, so the first part. If we say differentiation is the process of finding a derivative or a gradient function. Right? And we also use this a word called f prime of x is derivative of f of x with respect to x. This word with respect to is quite important because right now we're using x and y all the time, so there's no problem. But later on, we might have some questions that involve way different variables, especially when we talk about related rules. When we have like different units, volume or time and stuff like that, we're not going to use y and x. So we just need to make sure that we understand that when we're finding the derivative of something, or when we're differentiating, we're always finding it with respect to a certain variable. What it means is that while you're doing the derivative, we're looking for that x variable, that variable that you chose, and then we're differentiating with respect to that. It also comes very handy when you're doing integral calculus, which is the opposite of differentiation. That also matters about what variable. Lastly, sometimes later on, if you choose to take upper year like physics or math, we'll have some functions that takes two values. For example, you can have a function that like we're not doing this, definitely not. You can have like z equal f of x and y. Then we have two possibilities. Take this d of f or d of z divided by dx or dz over dx. That means that we're differentiating with respect to x. We can also do this dz over dy, and it means that it's differentiating with respect to y. So it's very important that we understand that we're finding the derivative with respect to a certain variable. By the way, when we're doing this, the other variable that may be there has no effect. For example, if you have some kind of expression as like 2xy, if you're differentiating 2xy, then if you're differentiating with respect to x, y just doesn't matter. Like it's not doing anything. It's just x that we're looking for. Does that make sense? Anyhow, keep in mind, this concept will be there later on, so keep an eye out for that. Especially when we do implicit differentiation, which is not too far. Yay, factor J, so content J. Okay, so let's talk about some basic rules of differentiation. First part, if you have a constant, whenever you have a constant and you differentiate it, okay, from this table, this arrow means differentiation. Move down a bit. Whenever you differentiate a constant, like 5 or 10 or a or something like that, that's 0. Whenever you have a variable alone with an exponent n, that exponent n comes down to the front, nx. Then we deduct the exponent by 1. So we do minus 1, becomes n minus 1, the power. So once again, x to the power of n, differentiate it, it becomes n times x to the power of n minus 1. Because of this minus 1 feature, I think of differentiating kind of like going down a step. Going down a step by step by step. If I had to use my hand position to describe the differentiation, differentiation is kind of going downwards. Why? Because the exponent goes down by 1 every single time. That, it ties with the first rule that a constant goes to 0. If you have a big polynomial, if you differentiate it multiple times, ultimately it will go to 0. We'll see that in a second. Next one. Let's say we have a function that is in the shape of c of u of x. Okay, so c of u of x is just a fancy way of saying like 2x or something, 3x squared or something like that. When you have a constant time of some function, or in other words, if you have a coefficient, I think it's just better to say coefficient here. Coefficient, unlike the constant, it stays there. It stays there, it just lingers on. So then we simply find the u prime x with c still there. So think of the c as a hi Andy, it's okay. Welcome to, you're the first person to give a chat here. Welcome, Andy. Kenta, please mute your mic. Sorry, I just saw that. Anyways, so coefficient is just lingers there even after you differentiate. So think of it like think of like a mosquito bite. So mosquito bit your skin, but it swallows. Even after you take a shower, it's still there. It's kind of like that. I don't think Jake is happy. Yes, Eric.
Is u of x just like a function of x, like similar to f of x?
Yeah, yeah. So for
So like
example, yeah.
it could be a polynomial or something.
Yes, yes. So for example, let's say we have 3x squared. Okay? Then we can think of this as 3 times x squared. Right? So then when we differentiate it, actually, yeah, okay. So we can think of it as differentiating the 3. Well, 3 is a coefficient, so 3 stays there. And then we only find that differentiates the u of x. The u of x was x squared. Now x squared is x to the power of 2, so the 2 goes down, and then the exponent 2 minus 1, so it's 1. So this becomes 6x. Does it make sense? Yeah, Jeffrey?
And what happens in cases, for example, if it was 3x squared plus x? Or 3x cubed plus x squared?
Okay, so we're gonna have 3x cubed plus x squared like this.
Yeah.
We'll do that example right after we've talked about the fourth rule. The fourth rule it's called an addition rule. So if you have u of x plus v of x, then if you find the derivative of this, we just simply find the derivative of u of x and derivative of v of x, and we just add them together. So if it's addition, it's very simple. X plus v prime of x. So the example that Jeffrey asked is exactly like this, right? So we simply copy this down here. So then we can take this into the derivative of the first part, 3x cubed. 3x cubed, so think of it as 3 times x cubed. X cubed, x power of 3, 3 goes down. And then 3 minus 2 on the top. So the first term goes like 3 times 3x squared. Second part, x squared, x power of 2. 2 comes down. It's 2 times x power of 2 minus 1. So it's just x. Which is 9x squared plus 2. I think we need some practice for this, so let's try some questions here. Okay. Let's follow along the example number 1, and then we'll do example number 2. Examples. Okay, so for the first part, I'll do the first part slowly, but if you want to go faster, you can know that f of x is equal to 5x cubed plus 6x squared minus 3x plus 2. That means that f prime of x, or dy over dx, however you want to call it, f prime of x is equal to, let's look at the first one. So 5x cubed, so 5 stays there. What about x cubed? X cubed, 3 goes down, then 3 goes down to 2, x squared, plus 6 stays there as a coefficient, x squared becomes 2x, minus 3 stays there. What about x? If it's just x, it means that we have an x to the power of 1. What happens to that one? Well, 1 goes down, and then the exponent, 1 minus 0 is just 1 minus 1 is 0. X to the power of 0 is just 1. Just 3 times 1. What about 2? 2 is a constant now. If I find the derivative of 2, 0. Then let's reorganize this. 15x squared plus 12x minus 3x. Sorry. 3. Yes, Borna?
Why does the second rule work? Like the one where you bring the exponent down?
So you can prove it. How it works, you know it works if you try to use the first principles of calculus. All the skills that we're learning in this topic, as I said, this topic is about skills and tools of how to find derivative, right? How all the things that work here are always provable by using first principles calculus. So if you wonder how it works, try the first principles calculus. First principle calculus means that limit of h goes to 0, f of x plus h minus f of x divided by h.
So you put x to the n inside that, and then it like
Yeah,
goes
so
to
for example, if you want to prove that x power of n thing, then we go like limit of h goes to 0, and x plus h to the power of n minus x power of n divided by h. Prove that, you go through this, then you get n x power of n minus. What? I think it might be a fun one to do. Let's do it. Every now and then. That's just very interesting. Proof. I wonder if I can do it. I haven't done it for a long time. Prove that d over dx of x power of n is equal to n x power of n minus. That's my goal. So let's do that. Limit as h goes to 0, f of x plus h minus f of x divided by 8. 0, x plus h power of n minus x power of n divided by h. Okay. I think if I expand, so I think I'm using the, what am I using here? What do you see? Anyone want to shout out?
Binomial expansion.
Binomial expansion. So I'll just do the first couple terms. We don't need to do everything. It's become x power of n. Then the next one will be what? N choose 1 or something. Was it like that? N choose times x power of n minus 1 h. Then it's n choose 2 x power of n minus 2 h squared dot. Right? Do you remember this? We don't need to do a whole lot. Soon we'll like so okay. Plus n choose n times x power of 0 and h power of n, right? And then we do minus x power of n on the top at the very end. Now we can cancel out the x power of n part. Then it comes like this: n choose 1 times x. Dot. Now in this good world that we can cancel out the h entirely. So that h is cancelled on the bottom. H goes it's gone there. 2 becomes 1. Everything goes down, and last one also goes minus 1. And then we realize now we can take the limit. Apply the limit, then it becomes n choose 1 times x power of n minus 1 plus and then what happens next? All the other terms always have an h of some sort, whether it be h squared, h cubed, h power 4, blah blah blah, all the way to h power of n minus 1. They all go to 0, so that's it. This is the limit. N times x minus n minus 1. Now we have by, what is it called? By deduction. That's why it works. Okay. Okay, so let's try, why don't we try one question from here?
Can we do the B as well from
I
example
think,
1?
yeah, I think we should do example number 2. Prepare for that. It's a bit more difficult. It's more interesting. Okay. I'll do A and you do B. Okay. 3 f of x square root of x plus 2x. Okay, so initially it doesn't look, it's not a polynomial function, but it is kind of. it still has that formation of x power of n. Notice that unlike the polynomial function, we didn't have the limitation for the n value. N value could be anything. So just going to do whatever we want. This time let's use the d f of x, right, d over dx, just for the diverse notations. First thing that I would have done was to switch this into 1 over 2 here, and then 2 times x power of negative 1. Then we can find the derivative of this. 3 times 1 over 2 goes down, and then 1 over 2 minus 1, plus 2 times negative 1 down, x power of negative 1 minus 1 will be negative. This will be over 2 x power of negative 2 minus times x power of negative 2. If you don't like the notation of this, so I don't know what you prefer. Square. See how we can just do this again. So basically the hint is, it's always the same problem solving technique, right? One of the problem solving techniques that we know is that we want to make things look like what we know. We want to make it similar to. It's like human biology. We're attracted to or similar to it. Oh, not quite. But that's the idea that we're using. Jake is always going, controversial. Anyhow, we want to make it similar to us, which means that we want to make it look like x power of something. So whenever you have those square root of x or over x or whatever weird things, make it look like x power of something. And life is happy. Hopefully you've had some chance to practice solve part B as well. There are tons of questions here. Why don't we try the number 6? Only because they have different variables. Let's try these two. So once again, these two are essentially just the same thing, except they just have different variables. I'll do the first one, second one, as usual. dt over dt. D big T over d small t. So, okay, before that, I'll just rewrite t as power of 1 over minus times t power of negative. Easy. dt over dt. 1 over 3 goes down. T to the power of 1 over 3 minus 1 is negative 2 over 3. Minus 2 times negative 2 times t to the power of negative 2 minus 1, negative 3. This will be 1 over 3 t to the power of plus 4 times t to the power of negative 3. I can rewrite this as 1 over 3 times negative goes down to bottom, the cube root of t squared. What a weird. Plus 4 over t to the power of. I'll give you a bit more time to do part D. $19 people. Someone else joined, I think. Morning, everyone. Once again, this session is being recorded and on YouTube. I'll link that. Oh, also,
You famous?
yeah, I'm already famous, but you'll be famous as well. Your voice is being recorded as well. Your face is not being recorded. suddenly realized background. Checking if it- Too much, I think. I think it's fine. Nothing weird. Nothing weird. Do you, I think it's all fine, right? Okay. Anyhow, let's resume. Any questions about part D? Otherwise, let's move on. I don't think we have to do it. Okay, let's move on. Part B. Yay, chain rule. Chain rule. Okay, so chain rule is kind of like, okay, so I don't, okay, a bit of background, history, analogically. I don't know if it's true for everywhere around the world, but I know at least in Korea, in like long time, like 500 years ago, when let's say let's say you're like a head of the family, and then you committed a crime. Say killed someone, or you assaulted someone, or you stole something, or you insulted the king or something, and then you get jailed. Of course, you get caught, you get jailed, but then you're not the only one being punished. There's this idea of like chain. It was kind of a chain rule. I don't know. Like I know in Korean, it's like if you're sitting next to them, you also get that. So then, not only you get punished, but your spouse and your children also get punished. It was like a thing. Also, like there was like a phrase that if someone's really bad for you, like oh okay, how about this? If you're a servant of a king and the servant betrays the king to go to the other side, the king goes super furious and they go like, let's kill 3 generations of you. So they go to the family and they kill everyone, including them, their generation, their children's generation, grandchildren's generation. You support it? No, it's so sad. But yeah, it was like a thing. That's kind of an idea of chain rule. A chain rule is that when you take a derivative of something, we not only take the derivative of what's outside, but you also take the derivative of what's inside. This idea of the chain rule closely relates to the idea of a composite function. Okay? Remember the idea of the composite function? If you have, let's say, g of f of x, by the way, we can also write it as g of f of x like this, which I don't really like. I don't like this goff thing or fog thing. But anyhow, if you have a chain rule or an expression like y equals g of x, g of f of x, then first thing we do is we take the derivative of g of x first. Sorry, what am I? G prime of f of x. That's what it looks like, right? G was the fault, like not a faulty one, but we're attacking G. Yeah, G is taken down. But what about f of x? We also kill the f of x? Yes. And then we add f prime of x afterwards. Is that how you do it? Sorry, not add, sorry, my bad. Multiplication. And yes.
Is it y equals that, or is it dy
D-
over dx equals that? Okay.
Thanks for. Okay, do you understand the idea? We first attack outside shell, and then we attack the inside shell. I don't know. Maybe for as a student perspective, it was quite difficult. But after I learn more about calculus, I think it's really satisfying. Chain rule. Feels like it's a complete kill kind of thing. Also, it kind of feels like a chain reaction. Okay, so let's take some examples of. Okay, so the chain rule is y equals g, and u x, and du over du times du. Okay, so this is what it says on the textbook. I'm not really sure, like, because this u thing is quite complicated in my mind. So I don't know. I don't know how to think about this. But the idea is that, like it seems like it's dy over du times du over dx. So it's like du are cancelled out. Like what? It's kind of weird, but that's how you see it on the formula book. I wonder if I can find the formula. Oh, by the way, we have that f x power n derivative n x power n. Chain rule, yes, okay. So we do have it as y equals g of u, where u equals f of x, du over dx is equal to y over du times d over dx. So we see the chain rule right there. Now let's take some examples of chain rule. Let's take some examples of. Okay, so the first thing that I'll do for any questions is, of course, you can get faster, is to identify what is g of x, what is f of x. I think it may be better if you declare the f of x first, because f of x is what's inside. What's inside the shell? In my opinion, what's inside the shell for part A is the 4x minus 5. I'm going to say that u equal to f of x. Is it? Wait. U equals f of x. U equals f of x is 4x minus 5. If u is 4x minus 5, then what is g? What is g of u? Now, what it means that we can replace that 4x minus 5 with u, then g of u is just u squared. Now we've broken these into pieces. Let's find derivative of dy over dx will be equal to, first we find the g prime of u. Or multiply by the u prime. Or in other words, we can say this dy over d times d over d. Notice that dy over du, it's a differentiating y with respect to u. With respect to u. Anyhow, what is a derivative of u squared? 2u times, what is a u prime? It's quite easy. 4. What is u again? Place u x minus 5 times 4, 8, 32x minus 4. Once again, it's important that we identify what is f of x and what is u, f of x, and also what is g of u. I think it's always easier if you try to identify what's inside the bracket first. It's always a rule. Let's try another one. Why don't we try what looks more interesting? Should do like g. Let's try g. y equals 6 over 5x minus 4. Another quite a straightforward one. I think whenever you see a bracket, it's quite straightforward, right? Think for this. U equals f of x, 5x minus u of u, 6 over squared. Well then, dy x, y over x, dy over dx, 6 times 6 over u squared is 6u to the power of negative times negative power of negative times d over dx will be 5. Then will be 30 negative 60 times u, it was 5x power of negative 60 divided by 5x minus.
Previous example for a second.
Fancy thing. 어머. 잠깐만. Give me a second. No one saw anything, right? Saw anything. Okay, should we do one more example? Let's do one more. Should we do some questions and let's do a bit more harder one. Oh, look at 7. It's very enticing. Should we do 5 or 7? Okay, let's see chat. 5 or 7? 7. Out of 19 people, 17 people, 3 people responded. That's a great majority. Chat. I didn't know, but I've only thought the word chat was just used for like actual streaming. But I like, and especially grade 8 kids, they just use the word chat just all the time. It's really weird. Like they refer to each other like their friends. Chat. Pro streamer. I used to stream. I think I told you before. I used to stream on Twitch and YouTube. There's one time I was streaming the Portal, the game, and this weird person just came in. Like until then, only people who comes into my streaming was my friends, right? Then this weird person came in at the beginning of the game, and he stayed there for the entire game. And at the end, I was like, "Hey, who are you?" Oh, he's like, he really loves Portal. He goes around to see newbie players who play Portal for the first time. Just finds it fun. I think it was quite weird. My experience. Okay, right. Let's try 7 due to popular demand. Suppose that looks fun question. Okay, suppose that f of x is equal to 3 times ax minus b over x to the power of 3. given that f of 3 over 2 is 3 and f prime 3 over 2 is 30, find a and b. All right. Okay. Before we even start this question, what do you feel? We're supposed to find a and b. And we have two information. What does that sound like? I'm looking at chat. Looking for this expression. I'm looking for two things, and I'm given two hints. What is that? This is the quietest chat ever.
Well, for the first one, you can just plug in 3 over 2 into the equation.
I know, but like what does this go? Where does this go? It's a 3-word phrase. Or 2 words phrase. We just did it before this topic. Systems of solving simultaneous. Thank you, Kenta. So Kenta can work on the spelling, typing skills. Mr. Kenta. So we are doing simultaneous equations of some sort. So let's do f of 3 of 2. F of 3 over 2 first. So f of 3 over 2 equal to 3 times a times 3 minus b over 3 cubed. Okay, that looks kind of weird. Ugly. 3 times over 2a minus b over 3 over 2 is 2 over 3 times b. 2 over 3b cubed. It doesn't look so good, but it can happen somehow. Should we expand this? Okay, I'm gonna hold it just in case. Just in case it works out better. I'm just gonna hold on to this. But let's try to find f prime of 3. The first thing that I want to do is grab this, put down here. So first thing I have to do is I need to find the f prime. Right? So once again, for my f of x. Hi Jeffrey.
If we find the derivative of the function, wouldn't it become a simpler expression? Then we can plug the number. Oh, wait, no. Okay. Yeah, being stupid.
So for f of x, let's try to identify what's inside there. So I think the first part, the u called ax minus bx, obviously. Then the g of u can be called 3 cubed. I'm going to use a chain rule to differentiate f prime of x. Then f prime of x is going to be g prime of u. Prime of u, 9u squared, using my multiplied by u prime. Prime will be a prime or a minus, this is b over x, this is times x power of -1. So it'll be plus b times x power of -2. Right? It's dirty. Space. What is 9 use? U was ax minus 9 times ax x squared times a plus b x squared. That looks very dirty. But apparently, if I plug in 3 over 2, oh, I forgot. This was 3. And the last one, this one, if I plug it in, it will be 30, right? F prime 3 over 2. B over x. And it can be faster here. This is 2 over 3 squared times plus, sorry, my bad. a plus b times b over 2 to the power of -2. -2 makes it the denominator, so it's kind of reciprocal. It'll be 2 over 3 squared. I think I'm going somewhere. See it? I can tell.
So are you for the f prime part? Are you plugging in 3/2 into a? Is that? Wait,
Oh, sorry.
wait.
I plug into x.
Yeah. Okay. That's okay. Yeah.
Okay.
Thank you.
Now let's summarize what we know of. So first thing that we know is that 3 times 3 over 2a minus 2 b to the power of cubed is 3. We also know that 9 times a minus 2 over 3 squared times a plus times 2 squared 30. I forgot the b. It's like a very dirty question. But we do have 2 equations, and we do have 2. I'm pretty sure we can go somewhere from here, right? Let's see. What I can do. Okay, maybe I'll try to divide the second one by 3. I have an idea. Okay. So let's undo the. If I look at the first part, it's 3 times something cubed equals 3. What does that mean? It means that 3 can be divided from both sides. It'll be a minus 2 cubed equals 1. Well, we can cube root it. A minus 2. What does that mean? It means that we can plug in. Means that this line, this weird thing squared, is also just going to be 1. So call this row 1 and 2. It'll be 9 times 1 square, so it's just 1 times a plus b times, or let's rewrite b as 4 over 9. It's 30. Then it's 9 times a plus 9b. Then we can say that a plus 9b 10 over 3. Aha! Now, the systems of equations are a lot simpler. We have systems of linear, because our a's and b's are all just all. I don't have a calculator with me. It's at school, so I'm not able to use a calculator. I'm just going to do it manually. First thing that I'll do is for row 1 and row 2, both of them, I'll multiply the equations with some numbers, so we don't have any denominators. Over 2a minus 2 multiplied by 6, it'll be 9a minus b 6. I think we're good. Row 2 I'll multiply by 9, so 9a. Oh, 9. 3. Okay. Then I think it's very naturally we can minus. It'll be negative 8b4 and a minus 12 plus a equals 2. Voila. Yes, yes. A equals 2, b equals 2. Okay. We good with this? We can plug it back in. I think we're good. I think having that guideline of what direction we're as soon as we see it, it's quite important. Okay, so that's been doing this for an hour and 15 minutes. An hour and 12. So at this point we can stop. We'll stop there. Father has to work, so I have to empty out. Any questions before we finish?
Yes. Can you hear this?
Yes, I can hear that. Yeah. Mute Jeffrey for everyone in the call. Nice. So mute is Jeffrey is muted for everyone, so no one can hear Jeffrey now. Wait, I can't undo it. No way. Wait a second.
No.
Okay, never mind. Okay. I almost clicked kick out. Don't watch.
Whoa.
Wait,
Is that in the recording now?
the audio is there. Okay, Jake. Okay, I'm really sorry, but Jake, I'm gonna start watching you. Okay. So prepare your camera. Wait, no way. I did not know I can do that. I think I can undo your camera. Anyone's camera. It's kind of crazy. But I can't unmic someone. It's funny. Borna, can I don't watch you? It says don't watch. I think Borna's asleep. Alright, anyhow. Any other questions before we finish? Alright, if you have no other questions, we'll finish there. I'll stop recording.